So my presentation today is based on work done by one of my students, Michael Winkler, who graduated a couple of years ago. We were looking at the question of tunnel ventilation, obviously, given the scope of this conference. And the question was, is there ever a circumstance, if there's a fire in your tunnel, when the appropriate response is not to use the ventilation system? So as I say, should we use tunnel ventilation during a fire incident? Normally, strategy in all our tunnels is, if there's a fire, we turn the system up. We turn it sometimes right up. Why do we use that strategy? Well, research has shown that uncontrolled smoke in a tunnel moves faster than people can walk, sometimes even faster than people can run. People have to get out, so we control the smoke to give them a smoke-free egress path. Good reasoning, but do we always need to do that? Do we always need to move faster than smoke? Because the concept comes from road tunnels. And this is the scenario where you have a queue of vehicles building up in a tunnel, and one of them is on fire. And obviously some smoke is produced, but the vehicles ahead of the fire can move out of the way. And so we think, okay, well, here we've got a queue of vehicles on one side of the fire, so we want to control the smoke so that all the smoke's pushed away. So that the remaining racers there in this picture can safely egress from the tunnel. The strategy, the ventilation strategy, is to protect the queue. And the concept works well for road tunnels. The question that I'd like to pose is, does it make sense for rail tunnels, for passenger trains in particular? Because if there's a fire at some random point on a passenger train, which side of the fire is the queue that we need to protect? The vehicles ahead of the fire are part of the same vehicle, so they can't simply get away. And so we have the situation with the fire in between two groups of people. So what happens when we turn the ventilation system up? Or, really, what happens if we were to turn the ventilation system off or keep the ventilation at low level? That will have effects on a number of things. It will affect the fire, but how? It will affect the smoke, but how? It may affect the people. But we need to understand how ventilation affects each of these categories, and then we put them all together, and then we'll see how things work out. So in this kind of fire emergency, where the train has stopped in the tunnel, and I'm not considering the possibility that the train can carry on safely out of the tunnel and then evacuate, that's a separate issue entirely. But if the train stops in the tunnel, we have a number of options for our ventilation system. We could not use it. We could choose to minimize air movement, so there's possibly some natural flow in the tunnel due to pressure differences, due to piston effects and so on. We could choose to use our ventilation system to cancel that out. Or we could blow gently from one side. Which side do we pick? Or we could blow strong from one side. But again, which side do we choose? What effects do these strategies have? And also, what do you expect or instruct passengers to do? Although I don't really have time to go into that question too much in this presentation. The issues are, ventilation affects fire behaviour. The fire will behave in a different way if we blow on it from if we don't blow on it. Fire produces smoke. I'm sure that won't come as a surprise to any of you. Ventilation, as we know, affects the smoke. The smoke generally affects the people. Sometimes the fire affects the people as well. Which of these effects is most important to us? There's lots of question marks in here to do with where the smoke goes. How toxic is it? How does the fire grow? How does the fire spread? What's the fire size? What's the fan power? You know, there's lots of questions going on. And the solution to our problem can only be found by actually considering all of these questions together. It's no use simply looking at the question of ventilation for smoke control, assuming that the fire will not change, because we know that the fire does change if you change the ventilation. We need to look at every single aspect. I'm not really going to get into the question of how ventilation affects smoke. There will be plenty of presentations probably at this conference, and I'm sure you've heard many more before about how we need a certain amount of longitudinal flow to control back layering, to control smoke, and so on. But ventilation pushes the smoke around. We know how that works. But the question is, what actually is smoke? Well, I've said here it's a mixture of air gases, fire gases, and sooty particles. And when you blow smoke with clean air, what it does is it produces more smoke. And that's one of the simplest equations I give in one of my fire dynamics classes at the university, is that if you've got X kilograms of fresh air and Y kilograms of smoke, and you blow, you end up with X plus Y kilograms of smoke. We just produce more smoke. And also, generally speaking, stratification is destroyed. We blow that one way, we end up filling the whole tunnel. But how does ventilation affect fire? And again, I'm not really going to get too much into the question, but we know that as we blow on a fire, it grows. There are different types of fire that react in different ways, but you blow on a fire, it gets going. Every sort of Boy Scout, Girl Scout knows that. If you want to get a campfire going, blow on it. But also, ventilation affects fire spread. It affects the maximum size a fire can have, and so on. Here's two heat release rate graphs from train carriages carried out in fire testing of train carriages carried out in tunnels. And aside from the fact that there were obviously different types of carriages that were involved, the main difference between this fire, which as you can see here, grows from 0 megawatts to over 30 megawatts in about 5 minutes, burns out quickly and then dies off. And this one, that grows from 0 to about 12 megawatts in 20 minutes, two very different growth rates, but gives you a much longer burning duration. The difference between these two fire tests is that the ventilation was blowing at that one, and the ventilation was not blowing at that one. If you look across the history of every time someone set fire to a vehicle in the tunnel, they tend to produce a heat release rate graph if they've done it in any vaguely experimental conditions. These ones up the top, these are Runehammer fires that you're probably familiar with in the Hammerfest HGV test on top of it. These ones, a mixture of bus fires, train fires, carriages and so on. Every single one of these had a mechanical ventilation blowing at it. And you see basically the same pattern. Very sharp growth to a fairly high heat release rate that burns out fairly quickly in the space of half an hour or so. 3 tests, however, in the literature from naturally ventilated fires, much slower fire growth, much smaller peak heat release rates, much longer durations. The thing is, when we're talking about egress, sometimes we're only looking at the first 10, 15, 20 minutes. We're not, from a life safety point of view, I don't really care what happens 60 minutes in. If I've got a tunnel with cross passages, which is the case that I'm looking at here. So ventilation, we know, does give us some degree of control over smoke, but also it often results in negative effects with regard to the fire. Fire grows faster, gets bigger, and is much more likely to spread. The question is it worth using ventilation? Does ventilation make the tunnel safer or not? Now also, blowing on a fire, does it make the smoke more or less toxic? Well, we know we blow on the fire, we make the fire bigger. But if we don't blow enough air, we make the smoke more toxic. There's a trade-off here, which effect dominates. So in our study, we essentially put all these different things together. And I have to give a disclaimer at this point. The study that I'm talking about and the conclusions drawn from it relate exclusively to a single case. And that is the case of a fire on a modern high-speed passenger train coming to an uncontrolled stop, and I'll explain that phrase in a moment, in a tunnel with cross passages for egress. If there are no cross passages for egress and people have to spend longer in the tunnel, then these conclusions do not apply. So please do not try and transfer these conclusions to metro systems or tunnels without cross passages. What do I mean by an uncontrolled stop? Well, generally speaking, if there's a fire on this sort of train, in this sort of tunnel, what the driver tries to do is he tries to stop the vehicle so that the egress doors line up with the cross passages. That is, people getting off the train have a few metres to go before they're in a relatively safe environment of a cross passage. What I mean here is an uncontrolled stop where that has not been possible. So we're only dealing with a tiny fraction of possible incidents. And because this is an uncontrolled stop, it's kind of tending towards a worst case anyway, I'm going to make the worst case assumption, I think I'd probably say that in the next slide actually, I'm going to make the worst case assumption that the fire ends up right beside one of the cross passages, rendering that cross passage unusable, meaning that people have to go the maximum distance, which for our study we based our dimensions on the cross passage distance in the channel tunnel, is about 375 metres of egress. Now the way they're going to do that, and again this is a very specific case, is they're going to egress along the train away from the fire. They're going to get to the end of the furthest away carriage, either carriage 1 or carriage 18, we consider an 18 carriage train, and that's the point they're going to get off the train, and then they're going to progress in the tunnel towards the cross passage. So essentially, what I'm interested in here is what is the tenability conditions like here if we blow on that fire, or if we don't blow on that fire. I get into this in the paper, I'm not really going to say too much about it. We did a CFD study, and we used FDS. FDS is not very good at tenability calculations, so we did those in post-processing, making a number of assumptions that you can read about in the paper. We also had to take into account how fast people walk, and we took the walking velocities based on hand calculations. We didn't do an egress model, we did hand calculations based on results from the Metro project. Again, I go into more detail in the paper. The fire scenarios are different depending on whether we blow or not, and I realise that the red doesn't show up very well on this screen.
Unfortunately, something went wrong with the recording in the conference, and so I'm recording the rest of this in my hotel room a few minutes later, or later the same evening as it happens. So what we did was we selected a typical 18 carriage high-speed intercity train and looked at fires on 3 of the carriages at the end of carriage 2, so between carriage 2 and 3, between carriage 5 and 6, and between carriages 9 and 10, which is essentially at the midpoint of the train. We always made the worst case assumption that the fire was going to be beside a cross passage, meaning that passengers would have to travel the longest possible distance away from the fire, 375 metres to the next exit. So the distance travelled in the tunnel is slightly different depending on where the fire is. If the fire is between carriages 2 and 3, the people leaving the train from carriage number 1 have 40 metres to travel on the train, maximum, and then 335 metres egress in the tunnel, starting relatively close to the fire, whereas those coming from carriage 18 at the far end of the train have up to 320 metres maximum egress on the train and only 55 metres in the tunnel. Similarly, when we get to carriages 5 and 9, we have to see the different amounts of travel in the tunnel, as shown on the screen there. And of course, each of these egress points is considerably further away from the fire than it would be in the scenario of a fire in carriage number 2. Just before I give you the results, I have to give another disclaimer. The fractional effective dose numbers that I come up with here should only really be used as a ranking system, and they're not absolute values that give an accurate prediction. And so obviously those cases where the fractional effective dose is lower are preferable, but that doesn't mean if we have a fractional effective dose of 1, as you'll see in a moment, that it necessarily means technically that in reality you would be expecting fatalities at that level, although certainly we want to keep the fractional effective dose values as low as possible. So here are some results for a fire in carriage number 9, egress from carriage 1, although it's exactly the same as egress from carriage 18 because this is the midpoint of the train. And as you can see there, because the fire is growing so much faster in the forced ventilation case, that the tenability limits in the tunnel are considerably considerably higher. Let's get that the right way around. The tenability limits are lower, and that the fractional effective dose in the tunnel is higher. In the case of forced ventilation, whereas in the case of natural ventilation, because the fire is smaller at this stage, the net effect is less, and the fractional effective dose of the escaping people is considerably less. I have to say that the graphs shown here start at time equals 0 for each individual stepping off the train into the tunnel, and so it should not be understood that the first passenger leaves at the same time as the last passenger. There's obviously a time delay between those two, but we've calculated the fractional effective dose and shown it here just for that one individual as they walk through the tunnel. The results here for fire in carriage number 5, again egress from carriage number 1, you can see that the fractional effective dose under natural ventilated conditions is slightly higher than it was for 9, but still we're down at very low numbers compared to under forced ventilation, where the numbers towards the end of the egress path are tending up towards 1. As I say, don't take a hard and fast that a fractional effective dose of 1 equals lethal conditions, but certainly even with the error bars on the calculations, a fractional effective dose of 1 is something that we want to be avoiding if we can possibly manage it. When we move to the scenario of a fire in carriage 2, you see radically different. Under forced ventilation conditions, the first passenger is likely to be adversely affected within a matter of minutes, and is unlikely to survive until the cross passage. And the last passenger to leave reaches very untenable conditions very, very fast. Compare that with the natural ventilation case, and you'll note that the fractional effective dose is still only reaching up to about 0.1 at the end of the egress path there, simply because the fire is smaller, the smoke is less toxic, and so on. And in these calculations, particularly for the fire in carriage 2, it takes into account the thermal environment of the tunnel as well as the gases, the carbon monoxide and so on. So in conclusion, in an uncontrolled stop situation, irrespective of where the fire is, natural ventilation gives a more tenable egress environment than using ventilation. If the fire is close to one of the exit doors, using forced ventilation may actually lead to lethal conditions on the egress path. Whereas if the natural ventilation is used, both egress paths remain tenable for the duration of egress. Only conclusion we can come to, if there's any doubt, you must use natural ventilation. Do not use forced ventilation if in any doubt as to the location of the fire in the train. But I have to say there's no easy solution for egress from passenger trains, unless the fire is right in the front or right in the back, in which case we can simply blow the smoke away using longitudinal ventilation. But in a more general terms, to actually solve this problem, we needed to use a number of different models which interact with each other and make a number of assumptions which also affect the calculations. And actually we had to sort of put everything together and see what results emerged from the calculations. And I have to say, when it comes to fire problems, even the most simple problems can be very complex. I ended this presentation in the conference asking for questions, and there were a good number of questions. I'm not going to repeat those here, but we did get into discussions about whether in a real tunnel you ever can have a minimal naturally ventilated fire, or whether there's always some residual flow. And yes, I accept there is quite often almost always going to be residual flow, and so maybe the minimal flow conditions that we're interested in here are something that doesn't happen very often, but given the assumptions of this project, I think it was a good idea to stick with that. But anyway, I hope you've enjoyed this presentation. Sorry that my video recorded cut off halfway through in the real recording, and I hope, if this isn't YouTube, you can feel free to ask any questions down below. Thanks.